Okay. Well, thanks so much, everybody, for joining me to my talk. I'm happy to present work we've been working on for the last year on emulating Samsung's baseband. Before we get too into it, a little bit about me. I'm Grant Hernandez. I'm a recent PhD graduate from the University of Florida, and I work primarily on Android security and firmware analysis. And I just joined Qualcomm's product security team working on their modem. My co-author, Marius Mensch, a PhD graduate from Eurocom, he's a postdoc at FUSEC, and he works on building tooling for better dynamic analysis of embedded systems. Unfortunately, he can't be here today, but please just imagine he's standing right next to me because he was as integral to this work as I was. So let's talk a little bit about our agenda today. So I'm going to start with a little bit of a motivation as to why we decided to look at basebands. And to do that, we're going to actually go over some previous baseband work. Initially, we'll talk about how I started doing baseband vulnerability research and where it fell short. And then we'll jump right into reverse engineering the baseband firmware, how we built the baseband emulator, and then how we actually used our emulator to fuzz via AFL, allowing us to find end days and 0 days. Finally, we'll actually demonstrate that the things we find in our emulator actually work over the air, and then we'll conclude. So before we get really deep into the weeds, let's make sure everyone's on the same page. And I want everyone to know what a baseband processor is. It's effectively a dedicated device that is implementing the 2 through 5G cellular protocols. This pretty much allows you to walk outside of your house without a Wi-Fi connection and be able to get data, calls, SMS, and the like. And it really is the phone part of your smartphone. So the vendors below implement their own version of the baseband processor based off of the cellular protocols. These basebands run embedded firmware, and they usually leverage a real-time operating system to schedule tasks and maintain their real-time deadlines. And it's important to note that basebands are separate CPUs from the application processor found on mobile phones, whether it's Android or iOS, and this is likely due to their performance requirements. So why basebands? Well, basebands have a lot of attack surface. As I said, they support the 2 through 5G protocols, which are really complicated. Some of the things you can find on basebands include custom DSPs, ASN1 encoders, possibly auto-generated or written by hand, custom IP stacks, voice and audio codecs, X509 parsing, DNS parsing, and a ton more. The more you look, the more you find. Some things are really obscure and unique to cellular. Some things are things you'd only expect to find on a desktop. And another reason is that baseband attacks can be devastating. So imagine being able to compromise a baseband. At this point, if you're running code on a baseband, you can intercept calls, SMS, and all the data, independent of the operating system. And even if you're feeling really bold, you can try and escalate to the application processor itself, further compromising the phone. So it's an important attack vector to consider. Today, we'll be focusing on Samsung's Shannon baseband. This baseband is present on Samsung smartphones with the Exynos chipset, effectively non-US phones because the US phones use Qualcomm's chipset instead. It implements 2 through 5G protocols, and it uses an ARM Cortex-R to maintain its real-time properties. And it's an interesting vulnerability research target. It's been shown that there are over-the-air attacks that can be launched against the baseband itself. And it's also been shown that there are less than stellar exploit mitigations on the application than compared to the application processor. There's been 3 talks that are really good on Shannon exploitation: the Breaking Band talk, the Walk with Shannon, which went over a PANDA vulnerability in great detail, and even more recently, how to actually design a baseband debugger on device. So in this case, we'll be doing our debugging in our virtual environment. There is other baseband work too, but as you can see by the dates and the years, not as much as you would expect, given the importance of it on our mobile devices today. It's something that's in everyone's pocket, but really there hasn't been, in my opinion, enough focus on the impact of exploits and memory corruptions in basebands. The fact that I can put most of the top work on one slide should tell you that. And that's where really our work comes in. We developed a tool called Shannon EE. It's an emulation environment for the Shannon baseband. And what it does is it executes firmware directly, so no pre-processing such as a static analysis tool is required. You don't need a physical device, and it's scalable to as many cores as you have available. It is able to cold boot a baseband and brings up most RTOS tasks. Some of the core features include a Python API for prototyping peripherals and anything else you can come up with, ModKit and C-based FFI for extending and exploring the baseband, integrated coverage guided fuzzing via AFL, GDB for triage, and support for multiple SoC versions. So all in all, this gives us a really good platform, and I'm going to show it to you right off the bat. So all you really need to do is run our Shannon wrapper, at which point there's a config file which will be loaded, and it will tell which baseband firmware we're going to target. It will initialize the baseband emulator. It will apply hooks. You can introspect. It will boot the bootloader, jump straight to the main file. These are the log messages coming from the non-volatile memory initialization, and it will just continue booting, and it will start initializing tasks. And you can, at that point, start fuzzing or start exploring the baseband in memory, craft your exploits, and the like. So it's a real dynamic analysis platform for basebands, which, to my knowledge, there hasn't been one publicly released. But how did we get here? I think the journey of how we actually got this tool to work is more interesting than the tool itself. And I'm going to tell you how we actually achieved this. So it actually started last year around May, and honestly, probably a little before that. I had started to do kind of a discussion of what I could do to actually do baseband analysis. So was I going to go static? Was I going to go dynamic? I had seen a lot of static work, but I ended up trying to do baseband fuzzing over the air. I didn't have any experience with SDR or cellular, but I had a lot of reversing and exploitation knowledge under my belt. So how hard could it be, right? Well, cellular protocol standards are pretty much acronym soup, which makes things really hard to get into. I spent a whole lot of time wrestling with the physical aspects because I'm not a signal analysis person. Base stations, getting them set up, and then debugging why my phone wasn't working was a big headache. But finally, after reading and trying things out, I was able to get a test set up with a 2G base station and 2G and implemented the GSM and GPRS data protocols. I added a really dead simple bit flipper to the layer 2 to layer 1 code, so I would flip all packets leaving the baseband. I then connected a mix of phones to the network. I used an ADB logcat monitor to see if I could find crashes. And I found crashes, which was really cool. But then I now realized the main issue with this approach. I couldn't understand why they had crashed. I was just flipping packets randomly, and not to mention that the phones themselves weren't giving me the required debugging output to actually figure out what was happening, let alone the impact of what I just found. And on the right here, you can see a phone crash I got on a Samsung phone, and this is all it told me. It mentions, oh, there's a memory guard corruption, which sounds really promising. It's a heap overflow. But it has this thing, little symbol, it's like the word root. Looking more into that, and honestly, I should have probably listened to ComSecures. They don't recommend OTA fuzzing for more than just the fact that you can't get debugging output on basebands. It's just not a good approach. Looking more into the debugging side of things, I found that there are root checks within the baseband code itself. Pretty much, if your phone's been unlocked or rooted in a way that I guess is not using an exploit, the modem will no longer give you the debugging output that you would expect. So we're kind of stuck. To get modem dumps, we need root, but rooting suppresses modem logs. So how do we actually find, let alone debug these memory corruptions in a scalable way? The anti-debug makes this difficult. We would probably need some off-the-shelf exploits to bypass these things silently. Manual reverse engineering is an option, but basebands are huge. This doesn't really scale too well. And on the link there you can visit offline is kind of a demonstration of how much is really going on in a baseband. So from a vulnerability research perspective, my ideal setup would be GDB, coverage guided fuzzer, and snapshotting. So at this point, it seems like the most viable approach was to drop the over-the-air fuzzing and jump straight into emulation. To do that, we started by reversing the firmware. And this started by getting the firmware from a publicly available source. We bought a research phone, the Samsung S10. We targeted this specific firmware, And we also had a bunch of other firmware lying around, which we used this kind of flow chart to categorize. Pretty much, it's just the zip file, tar files within it. We pick one tar file, which has the modem code. Untar it, we have modem.bin and modem-debug.bin. There had been talk that actually these files were encrypted. We didn't see that. None of our images were encrypted. We were able to just throw it into Ghidra and get started. This format, the table of contents format, I'll show on the next slide. It's been well reverse engineered already. So it's a pretty simple format. The modem.bin file has a header. This header has a name, file offset, load address, size, CRC, and entry ID. And then this header is replicated for every entry within the TOC format. But for our purposes, we were really only interested into these two sections, the boot and main sections. Starting with the boot, we seeked forward into the file to find its start points. And looking into the actual code, we started to notice a very obvious pattern. If you've done ARM reverse engineering, the conditional flag is set. So this pretty much means the code is not encrypted, and we can just throw it into Ghidra and get started. Further disassembling confirmed these are the exception vectors, and at which point we can then jump straight into the boot, the reset exception handler, and get started. Doing some reverse engineering, disassembling, and naming, we realized that the bootloader is using UART, which is really cool, something we're going to emulate later on to be able to get this output, or pretty much liberate this output from the baseband. And we also noted two boot modes, the dump and the regular boot mode. And in order to do an emulation to be able to bring up this firmware in our Shannon EE system, we need to know who's signaling these boot modes and what boot modes are possible. So that brought us to a side quest into the Samsung kernel. Thankfully, because of the GPL, this is available publicly. I mirrored it here at this link, but effectively there's the modem driver within the code. We looked at it and two files stood out. The modem IO device file, which is actually the IO control handlers for the modem driver. And this allows for read and write. And then this link device memory file, which actually contains structs on the shared memory regions between the application processor and cellular processor. Looking more into the IO controls, there's something called CBD, or the cellular boot daemon. This communicates with the dev node via IO controls, and it actually will boot the modem up. It will do this by first resetting it, setting up security, setting it to on, booting on, download, which means it'll upload the code, and then boot off. The security request is actually interesting, and I'd like to talk about that at another time, but that pretty much enables secure boot for the modem. So looking more into this this link device memory file, we found a structure that's packed and is referenced in the actual IO, like it's an IO memory reference. So what this really means is actually going to be used for DMA and IPC. There are commands, and there's this magic field. This magic field actually matched, the magic numbers here actually match what we saw in the baseband bootloader, which means we can now actually map this same memory region in our emulator to be able to signal to the bootloader how we would like it to boot and allow us to explore the baseband and continue booting forward. As a side note, those other buffers, the format and the raw TX and RX buffs, those are actually receiving commands from the Samsung radio interface layer. So that's actually something we'd like to explore further, because that is really the IPC between the Linux kernel and the baseband itself. So with this reverse engineering out of the way, we actually had this nice block diagram we could make to help us understand kind of like how everything's organized and to make sure that we're all on the same page. So far, we had looked at these portions. We had looked at the modem interface, which is the host interface and via IPC, cross-core, and we'd also seen that there is UART. But there's a lot more to look at. We need the tasks that are specific to the cellular technologies. We need the other peripherals, and that brings us to our next step. At this point, we could actually start writing emulation code. But first, we need to pick our weapons. And for that, we chose Avatar 2, which uses QEMU as a target underneath. A little bit about Avatar 2. It's actually a Python framework that orchestrates other frameworks and allows you to interoperate between them. It allows you to define Python-based peripheral definitions for easy prototyping, which I really liked because it allowed me to work fast and not have to worry about compiling C over and over again. And it had a really nice interface to QEMU, such as GDB and its monitor protocol. So a really good thing to choose. And the first thing I did was I wrote a peripheral for the boot UART. It was really simple. On the right, you see this peripheral definition. There are two functions, the read and write functions, which are called if QEMU will access a memory address within the memory range that is defined on the left. Dead simple, and we were able to liberate the initial boot messages to help us debug our peripheral definitions from that point forward. And here's an initial video of actually it booting once we had done the UART. So you'll notice in the bottom left, there's some kind of debugging output showing us what's being done. And then you notice this is actually the UART coming out now, but look how slow it is. It's pretty much slower than a 56K modem at this point, which is okay. It's a good first start, but we definitely need to do better. So that's why we started going even further. And the first thing I did after seeing this was implementing snapshots, which ended up being a piece of cake with Avatar's frameworks because of it allowed us to remotely control QEMU. We could just send the command to do a snapshot. The only caveat is because we had Python and C-based peripherals, we needed to make sure we snapshotted both. So we just, pretty much the code you see here is exactly what we used to snapshot the Python peripherals at the same time as the ones in QEMU. And taking a step back, this is what we have so far, the first incarnation of Shannon EE. We have Avatar 2, we have our UART peripheral, we have the file parser for the modem images. We've been using GDB hooks up until now. And QEMU is our target, and everything is being done over IPC. But this is where the problem is. Actually, because this IPC is cross-process, and we're needing a lot of hooks and a lot of remote memory reads, these become the primary bottleneck. And we needed a way to actually solve this. But I spent a whole lot more time hacking on this, trying to improve the speed. And I kind of hit a dead end. I was like, something's wrong here. Maybe we need to take a different approach. So this is when I brought on board Marius. Who better to bring on than the lead developer of Avatar 2? So with him and his knowledge, he suggested we actually move to a different approach. We actually, instead of using QEMU, let's use PANDA. So we ported the rest of what we had done to PANDA. PANDA is just a fork of QEMU from 2013 or so. And what it offers in addition to QEMU is a plugin infrastructure, callbacks during QEMU's runtime state, and record and replay. And it's already integrated in Avatar 2's, framework. So the main issue is it still has the performance issues that we're dealing with. It's still a separate process. But that's when we discovered PyPanda. It's pretty much a library-based import of QEMU or a PANDA. You can literally import PANDA, and that means it's now a thread within your process. So no more IPC. You get a single Python interpreter with FFI to Panda's C functions. So you can do extremely fast native hooks, which allowed me to replace all the GDB hooks with Panda hooks. And we got a huge speed up doing this. The IPC was pretty much just a mutex waking up another thread now, which is a big speed up. And on the right, you see our block diagram of how things have changed. It's now all integrated together, and we can get higher performance, and we don't need multiple Python interpreters on either end. This is when we really start getting into the weeds of emulating peripherals. And we hit this function called PAL-init1. It's a huge monolith that pretty much boots the modem. Once you've gotten past the bootloader, you've gone into the main image, you hit this function, which brings up all the heap objects, the non-volatile items, the timers, DSPs, and all the tasks. So to kind of churn through this, we iteratively emulated the peripherals. We watched for crash strings or infinite loops. We used memory mapped IO monitoring to see which peripherals need more modeling, and it was really an iterative cycle. We also used some kind of simple cyclic bit pattern to kind of fuzz our way through some peripherals that were able to get us past any checks. And after doing all this, we had partially emulated the power management IC, the clock peripheral, a very, very small amount of the DSP, not the actual, just enough to the communication, the SoC driver, the Samsung IPC peripheral, the /shared memory, the timer, and the generic interrupt controller. So we could boot and we could bring tasks up, and we hit the banner. we had seen this banner in the static analysis, and we're like, if we can get to this banner, we'll be in really good shape. And we reached it. And this was about, I think, March. So it had been, I brought Marius on board in January and then in March. So things really kicked off and we're really cooking with gas now. So at this point, we had started to get tasks running and we were like, okay, let's start doing fuzzing. So we started to port Triforce AFL to our system. Triforce AFL is a patch set on top of AFL. It's originally developed in 2017. And what it does differently is it allows you to do system level fuzzing. So ShannonEE is a system level emulator, meaning it has a software MMU, and it invokes AFL from within the guest via hypercalls. And we combined this patch set with some AFL++ additions because it has some really good patches, which means we got better coverage collection and a persistent mode. And this allowed us to do fuzzing within using something called the AFL task. So to get an AFL task running in the baseband, we used our mod kit. We wrote a mod kit that allowed us to inject custom tasks into the emulated baseband, playing very nice with all the APIs that exist. We were able to write these in C, and we had dynamic symbol resolution for a nice C-like FFI. This was done cross version as well, so you wouldn't have to change our harness for let's say a 2017 firmware image to a 2019 firmware image. It would be seamless. And the diagram below shows you kind of how the AFL task is integrated. It has a couple of steps. It will set up the fuzz case, test case. It'll start the fork server. It will receive data from AFL. It will start the work collecting coverage. It will do the single fuzz test case, and then it'll call done and repeat. So now we actually needed to target tasks. So we integrated AFL within the RTOS itself, which means we could use the APIs that the RTOS tasks themselves already used. And this was an important thing that we chose to do because it would allow us to avoid rehosting, I guess, and carving out portions of the baseband to get our fuzz harness to work. We could just play nice with the messaging. And we reverse engineered the message and queues that were used to send data between tasks. And we would just call send message to target a task. On the right is the header of the queue items that would be sent. Very simple, source, destination queues, a size, and a message ID. So as an example, here is the GSM session management in the GPRS fuzzing harness. This is 2.5G/2G. This is what the data connections on our very early 2Gs would use. On the left is the queue item that's specific to the SM task. And on the right is the setup function for the task. This is important because we had to do an initial packet to send to the SM task, which would initialize it to the point where it would then be ready to receive radio messages. And it's important to note that our approach is skipping layers 2 and 1. It's jumping straight to layer 3, which saves us a lot of time with peripheral emulation. Here's the actual fuzz single. What it really does is very much the same. It will allocate a message queue item. It will allocate a PDU. It will get the work from AFL. It will copy it in, set the size, set the radio message ID, which will be reverse engineered, start collecting coverage, send the message. And this is an important part. It actually will send a message from task, the AFL task, and then the RTOS will reschedule directly towards a task. And we did this by actually setting the priority of our AFL task to the lowest possible. And then finally, once that message is done processing or any sub messages that return, it will call done work and do it all over again. So here's a video of it in action. It's just as how you would normally use AFL, and you can call it directly on the Shannon EE. It will spin up the fork server from a snapshot, so we don't have to wait for the whole thing to boot up. We can snapshot right before the AFL task is ready to run and the baseband is quiesced, waiting for events. It will load the initial corpus, start collecting coverage, and boom, it will start fuzzing. And our exec speed's pretty high because we've set a pretty high a persistent mode number. This does come at the expense of variable test cases, so you don't have to use it, but if you want to really churn through things fast, you can go ahead and do that. And now let's talk about the bugs we found. So before we jump straight into O-Day stuff, we wanted to make sure that we had built a tool that actually worked on real to find real bugs, not just kind of fake false positive bugs. So we decided to rediscover an end day. And we actually went off of Ahmad's talk, which was targeting a Galaxy, I believe, S10, or sorry, S7. And we were then able to build a harness for the same subsystems he fuzzed. So the GSM and GPRS radio packet handlers. And more specifically, we built harnesses for call control, CC, mobility management, and session management. These are all something you could read in the standards of GSM. We set AFL to the task, set up the fuzzer, and boom, we were able to actually rediscover the PDP network accept crash from a Walk with Shannon talk. So this gave us a lot of motivation, and we had pretty much done some ground truth testing on our emulator. Now to find new things. Once again, our target was GSM and GPRS because, hey, you know, if we find something here, this is the lowest hanging fruit. Why not look at LTE or 3G or even 5G? I mean, at the end of the day, if you're trying to compromise a baseband, you're going to go for the easiest target. 2G is that target, and it is still implemented in pretty much every baseband today. You can do a fake base station attack trivially. There's no mutual authentication, so it's easy to craft any message you like. Our coverage guiding fuzzing, we had some blank initial seeds, and we were able to debug coverage using PANDA, exporting coverage, and Giger's drag and dance. We didn't run even for that long, 30 CPU cores across 5 days, which further demonstrates the scalability. And we discovered 2 end days, the one from before and the one I'll talk about next, and 1 0 day, which we're in disclosure with Samsung about right now. And given the success of GSM, the fact that this is 30 years old at this point, we're still finding things, I'd say LTE and above is definitely next on our list. So let's talk about the other end day we found, which we're coining the call of death. It's pretty much I believe, a previously unknown overflow, at least publicly, in the call setup packet targeting this field called the bearer capability. This is something you can look up in the standards, but effectively it comes in when you're receiving a call. This packet was incorrectly parsed by the baseband when the call is incoming, and it's a heap-based buffer overflow, which we seem to have a fair amount of control over. And we did confirm that this vulnerability is no longer on newer firmwares. Balance checking has been added, and it's pretty explicit that they were fixing this. Whether it was from a report or an internal audit, we don't know. But the fact is we found it, and we were able to use Shannon to triage it. As you can see at the top here, our AFL task sent the message to the target task, which is the CC task. The CC task was scheduled in. It then received the setup message, which is noted as a radio message. It entered the decode function, and finally, later on, after some snips, you can see the length, which is pretty large for the bearer. It should be maybe only a couple bytes, and then it crashes with a PAL memguard corruption. If you remember, we had seen in the very beginning, we'd seen the PAL memguard corruption in the phone screen, but now we can actually see why this is happening and the backtrace to do it. But logs aren't always enough, so that's why we actually have the ability to use GDB. So we have the register R2, which is set to 30, 30, 30, 30, and we have this comparison, which is comparing R2 against all A's. This is actually the static heap cookie, and this check is going to fail, and we can see the payload here. And the reason it's going to fail is because this is our payload AFL generated. Everything that's not ASCII 0 is the message header enough to reach the bearer, and the rest is the bearer. So that's pretty much being copied straight into a heap buffer that is clearly too small. So to even further have confidence that what we built is going to work in the real world, we replicated what we found over the air. Our experimental setup included a Blade RF, which is about $420, a base station, Yate BTS, which we modified with our exploit payload. We literally just copied it in verbatim, maybe cut off the header, the very initial header, and that was it. We targeted the S10 and S7 in our testing, and we used SIM cards from Osmocom to help the phone get an easy connection. And shout out to Tyler Tucker, who is an author on this paper, on this work, who pretty much spearheaded this and made sure that I didn't have to go through the hell of getting this set up again. So he suffered for what you're about to see. And here's the demo. So the phone on the left and the phone on the right are both connected to the fake base station. Call on the left is calling the phone on the right. You can pick it up. and it will go through, but the phone on the right won't have the call working. For some reason, you get another call, whether you decline or answer. At this point, it's too late. The signal bars disappear, and that little X comes in, which means the baseband has crashed. At this point, it's a pretty cool thing we can do, and to even further confirm, we use logcat to get the logs. But as you can see, this is all you can see in the logs. You actually can't see anything else, so without ShannonEE, it'd be really tough to debug why this happened. So let's wrap things up. There are a lot of remaining challenges and I think future work for this. For instance, doing fuzzing for cellular tailored fuzzing would be really cool to get better code coverage. We ignore the physical layer, so what aren't we missing by supporting it? I mean, DSPs are attack surface too. And honestly, I think I would love to see this, a holistic analysis of baseband attack surface. What has been covered and what still remains? Some key takeaways. We really need scalable tools to keep up with all the cellular protocols, especially 5G, which is on the horizon. If we can barely do 2G, how on earth are we going to keep up with the rest of the 5 and beyond Gs? Building an emulator, even with undocumented hardware, can be done. We can bring this methodology to other basebands, and I think we should. And honestly, we have to emulate basebands. We need the right introspection level, especially to do memory corruption debugging, and over-the-air testing, I think we've shown, is just not going to do it. With that, we have some releases. We'll be releasing, the top link has all of our reverse engineering tools and code, Ghidra loaders and so forth, some firmware samples, an on-device log parser for the BTL format, and Shannon EE will be released at a later date after disclosures and some further QA. But you can watch that repository and you should be able to get an email when we do our first push. With that, I have to thank all the sponsors and people who funded this work, NSF, SRC, NWO, and the Air Force and Navy. Without their contribution and support, this work wouldn't have happened. With that, I hope you enjoyed the talk, and I would be happy to take any of your questions.